Hello, welcome to the course SJPHY2C02 Optics, Laser and Electronics. The contents of today's lecture is taken from Principles of Electronics by V.K. Mehta. We will continue to discuss topics from Module 4, Electronics. In the last couple of classes, we discussed about rectifier circuits which convert AC into DC. So if you look at the output of a half-wave rectifier or a full-wave rectifier, you will notice that it's not a clean AC, it's a pulsating, it's not a clean DC, it's a pulsating DC, meaning it has both AC and a DC components. Now, you can make it a cleaner by removing the AC components, and for that purpose, you use something called a filter circuit. So filter circuit removes AC component of the rectifier output and allows only DC component to reach the load. So you can see this is the layout of the filtering action. So you have rectifier output fed into a filtering circuit, and the output of the filter is given to the load resistance. So at the input side you have both AC and DC. On the output you have only pure DC. So this is the case of an ideal filter circuit. In the case of any practical filter circuit, it's not 100% DC. There will be a minor amount of AC component, but for all practical purpose you can treat it as a pure DC output. So typically a filter circuit consists of a combination of capacitors and inductors. By the way, inductor is also known as choke. Now before getting into the details of a filter circuit, let's first try to understand the working of a capacitor and an inductor. So you know that typically in any electrical or electronic circuit, to resist the current you use a resistor, or more precisely an ohmic resistor. But not only an ohmic resistor, any electrical component has its own resistance. So the only difference is that for an ohmic resistor, the resistance is frequency independent, whereas if you consider a capacitor or an inductor, its resistance is frequency dependent. That's why instead of resistance, we use the term reactance. So the resistance of a capacitor, the capacitive reactance, is given by Xc equal to 1 by 2 pi Fc, where F is the frequency of the signal and C is the capacitance. So if you take a typical AC signal like the one which comes to your household at 50 Hertz, so if you plug in the value for F and C, you get some finite value for capacitive reactance, which means the capacitor allows AC to pass through, but it will offer some resistance. In other words, capacitor restricts AC, just like an ohmic resistant. On the other hand, if you feed a DC signal to the capacitor, what happens? We know that in the case of DC, the frequency is 0. So when you put 0 in the denominator, the capacitive reactance become infinity. In other words, a capacitor offers infinite resistance to the DC flow, or it completely blocks DC. So capacitor allows AC to pass through with some restriction, but it completely blocks DC. When it comes to inductor, the inductive reactance is given by XL equal to 2 pi FL. Once again, for AC, it allows AC to pass through with some restriction. What about DC? For DC, F is 0, so inductive reactance is 0. In other words, it allows DC to pass completely. So if you compare a capacitor and inductor, capacitor completely blocks DC, inductor completely allows DC. When it comes to AC, in the case of capacitor, when frequency increases, the resistance decreases, whereas for inductor, when frequency increases, the resistance also increases. So you are going to use this particular characteristic of a capacitor and inductor for filtering the AC component from the output of a rectifier circuit. The common types of filter circuits are capacitor filter, choke input filter or inductor input filter, and the most popular one is a capacitor input filter, which is also known as the pi filter. So in this class, we are going to specifically discuss about capacitor filter and high filter. First, a capacitor filter. So this is the circuit diagram of a capacitor filter. So you have the output of a rectifier circuit. It could be a half a rectifier or a full wave rectifier. Then you have a filter capacitor C, which is placed across the rectifier output in parallel with the load resistance RL. So since the capacitor is parallel, the pulsating DC, for example, in this case, we are considering a full wave rectifier. So this is the output waveform. So the pulsating DC from the rectifier drops across the capacitor. Now, what happens to the capacitor? So you know the general functioning of a capacitor, right? So this is very much like the inverter in your house. So what does the inverter do? When there is power supply, it stores electricity. When there is no power supply, it becomes the source. It starts to provide electricity. So same thing happens with the capacitor. When there is power supply, the capacitor gets charged. When there is no power supply in the circuit, the capacitor gets discharged. Or if you take another analogy from chemistry, I'm sure you are familiar with donor and acceptor molecules, right? So capacitor can behave like both donor and acceptor. So when there is power supply in the circuit, capacitor acts as an acceptor. It accepts charges and stores in it. When there is no power supply in the circuit, it becomes the donor. It donates the charges back to the circuit. So that's the typical behavior, typical working of a capacitor. Now we can analyze the working of this circuit in terms of quarter cycle. So you can see that this is one half cycle, this is second half cycle, this is third half cycle. Okay. So we are going to split it into two quarter cycles. So you have quarter cycle OA, during which the signal increases. Then you have quarter cycle AB, during which the signal decreases. During BC, once again signal increases. During CD, signal decreases. Okay. Now, during the first quarter cycle OA, you can see that the rectifier voltage increases, right? So when voltage increases, it charges the capacitor. Also, it supplies current to the load. Now, at the end of the quarter cycle OA, the capacitor is charged to the peak value Vm. Now, what happens after this quarter cycle? The rectifier voltage is going to decrease, right? So you can see during quarter cycle AB, the voltage is going to decrease, and eventually this becomes 0. So it's same as the condition of there is no power supply. So what happens now? The capacitor becomes the source. It starts to donate charges. Okay. So ideally what should happen if there is no capacitor here? When the rectifier voltage decreases, ideally the load current should decrease. But now what happens? Now the effect of the capacitor kicks in. The capacitor starts to discharge through RA. In other words, the capacitor supplies the load current. Right? So in the previous quarter cycle, it was storing the charges. Now it is supplying the charges. Now, how fast the capacitor discharges? That depends on a parameter known as the RC time constant of a capacitor. So where R is the load resistance, C is the capacitance. So in this particular case, this is RL into C. So if RC time constant is large, then the capacitor discharges very slowly. If the RC time constant is very small, it discharges very quickly. Okay. So what you need to make sure is that the RC time constant of the capacitor is much higher than the time period of the signal. So in that case, what happens? Then the capacitor remains almost fully charged and the load voltage remains at Vm. And the load voltage decreases only slightly because by the time the next voltage peak from the rectifier comes, and that recharges the capacitor. So once again, I'll tell you what happens here. So during the first quarter cycle OA, the capacitor charges. In the next quarter cycle AB, it discharges. But RC time constant is very large. so the rate of discharge is very slow. So even though the voltage level decreases, it decreases very little. So for all practical purpose, we can consider the voltage to remain constant at the peak value. Now, by the time it reaches this point, the next quarter cycle BC starts. So during this time, the capacitor once again charges, so it goes to the peak value. In the next quarter cycle, it discharges. Once again, the discharge is very small, so voltage level drops only very little, and this process repeats. So the key point here, you need to keep the RC constant very high. So if you compare the input and output, you can see that even though there is some amount of ripple in the output compared to the input, it is very less. So you are making your DC output much cleaner by using a capacitor filter. Since the capacitor discharges very little between the peaks, the peak-to-peak ripple is very small. Moreover, as you can see from the graph, the output voltage is higher as it remains near the peak value always. So there is some amount of ripple. You can characterize that using the peak-to-peak ripple voltage, VR equal to I by FC. I am not going into the details of the derivation, where I is the DC load current, F is the output frequency of the rectifier, and C is the capacitance. So this is not a 100% pure DC, but the ripple has reduced drastically. A much more efficient method is to employ what is known as a pi filter or a capacitor input filter. So in the previous circuit, you had only one capacitor which is doing the filtering job. Here you have two capacitors and an inductor doing the filtering. So the filter capacitor C1 is connected across the rectifier output. Then you have choke or inductor L connected in series. Then the second filter capacitor C2 is connected across the load resistor. So here the filtering unit is the combination of C1, L and C2, and this looks like the Greek symbol pi. That's why the name pi filter. Now what happens here? So the signal comes to this point. So at this point, it meets the capacitor C1. As we know, filter capacitor C1 offers low resistance to the AC component of the rectifier output, while it offers infinite resistance or reactance to the DC component. So what happened? It blocks the DC completely, so the entire DC moves towards the inductor, while it passes most of the AC component back to the rectifier circuit. So in other words, the capacitor is going to bypass the AC component. Right? Otherwise, the AC component should travel through the entire circuit, but now it bypasses the AC component. That's why this capacitor is also known as the bypass capacitor. So from this point onwards, what you have, initially you have AC and DC. Now you have the entire DC plus some amount of AC moving towards the inductor. In the inductor or choke, what happens? Choke offers high reactance to the AC component, while it offers almost zero reactance to the DC component. So it allows the entire DC to pass through freely. And what happens to the AC? The unbypassed AC component or the AC component which C1 failed to bypass, it blocks a part of it. Okay, so at the end of the inductor, you have the entire DC plus very little amount of AC. Now you have another filter capacitor or another bypass capacitor. So what does this capacitor do? It bypasses the AC component which the choke has failed to block. In other words, it passes the AC component. So only the DC component proceed towards the load. So across the load, you get only the DC component. So this is the ideal situation, but in any practical circuit, the filter capacitor C2 will not be able to bypass the entire AC component. So a tiny amount of AC will be there across the load as well. So you can see in this output, This is not a 100% clean DC. There is a very slight amount of ripple, but this is much negligible, much smaller compared to the previous capacitor filter. Right? So for all practical purpose, you can treat it as a good DC signal. So you can see compared to a capacitor filter, a capacitor input filter is much more efficient. Now, before winding up, let's do a quick problem. For the circuit shown in this figure, find the output DC voltage. Okay, so you have a bridge rectifier. Its output is fed to a capacitor filter. Okay. So you have at the input of the transformer 115 volt RMS at 60 Hertz. The turn ratio is 10:1. So first you have to find what is the secondary voltage, and that's the voltage given to the bridge rectifier. So in bridge rectifier, during any half cycle there are two diodes which are connected in series. So if you treat them as ideal diodes, there is no voltage drop across them. But if you take any practical diode, for example a silicon diode, then there is some voltage drop across it which is equal to the barrier potential. For silicon it is 0.7 volt. So since you have two diodes, 2 into 0.7 volt is going to drop across the two diodes, and the remaining voltage comes here. So you call it as Vp in. This is the peak rectified full wave voltage applied to the filter. Okay, so you have Vp in here, and look at the configuration here. So you have a common point here, the ground is common here, which means your capacitor and the load are connected in parallel. In the case of parallel connection, the voltage is going to be the same. Okay. So this is the basic idea we have about the circuit. Now let's find out the values now. So first thing, we need to calculate the peak secondary voltage. So we know the equation. Secondary voltage divided by primary voltage equal to secondary turn divided by primary turn. So we are given RMS value. First let's find out the peak primary voltage. Multiply the RMS value with root 2 into 115. This is 163 volt. Then using the equation of the transformer, you can find the peak secondary voltage. This is 16.3 volt. So out of 16.3 volt in any half cycle, 0.7 drop across one diode, 0.7 drop across another diode. So the total peak full wave rectified voltage at the beginning of the filter circuit is going to be V peak secondary minus 2 into 0.7. This is 16.3 minus 1.4, which is 14.9 volt. Since this is a full wave rectifier, the output frequency is twice of the input frequency, 2 into 60, 120 Hertz. Now let's find out the output DC voltage. So the DC load current. So if you look here, we know that at the load only the DC component arrives, right? And the voltage is same across both capacitor and the load. So you have 14.9 volt across the load. So the DC load current is going to be voltage divided by the load resistance. So 14.9 divided by 2.2 kilo ohm, which is 6.77 milliampere. Now this is not a clean DC voltage. We know that there is some ripple in the voltage. So the peak to peak ripple voltage VR is given by I by FC, where I is the DC load current, F is the output frequency of the rectifier, C is the capacitance. So plug in the value 6.77 milliampere divided by 120 Hertz into 50 microfarads. So this is going to be 1.13 volt. So this is an AC component. So let's find its DC equivalent, which is the RMS voltage. So in the case of peak voltage, RMS value is given by dividing the peak with root 2. But now we have peak to peak voltage. So let's first convert peak to peak voltage into peak voltage by dividing with 2. then that particular value, when you divide with square root 2, you get the corresponding RMS value. So VR RMS equal to VR divided by 2 root 2. So this is 0.39 volt. So what is the output DC voltage? So you have the total voltage coming at the output is Vp in. Out of that, 0.39 is the AC component. So when you subtract the AC component from the total output, you get the total DC component. So VDC equal to Vp in minus VR RMS is 14.9 minus 0.39, which is 14.51 volt. So that's about filter circuit. In the next class, we will discuss about a special type of rectifier a special type of diode known as Zener diode, which is widely used in voltage stabilization applications. Stay tuned. Thank you.